Hey guys, welcome back. So last week we talked about vertical asymptotes and we talked about points of discontinuity such as holes and things like that. So the one we didn't really talk about horizontal asymptotes, and the reason that we didn't talk about horizontal asymptotes is because they are much harder to determine, much harder to determine. All right, the idea, all right, is that we're trying to find the restrictions on the range, right? So when we did discontinuity, we found restrictions on the domain, like what values of x can't x be, and that it leads to a hole or a vertical asymptote at x equals something. All right, so what we're trying to find when we're doing horizontal asymptotes, if you think about the idea behind it, it's saying we're trying to find what values of y don't work. Okay, so what are the things that we can't possibly get out of this thing? So again, much harder to kind of see, right? Because a lot of times that requires trying every single possible input and seeing what kind of outputs we get. And we're not going to take the time to do that. Okay, so realistically, to understand why, we kind of need a little bit of calculus to do it. So we're not really going to go into that much detail on the kind of why, right? So we're just going to kind of learn how to determine these. Okay, so if we have some rational function here, f of x is equal to g of x over h of x, all right, and let's just assume g of x and h of x are polynomials, and we're going to say, hey, you know what, the degree of g of x is m, and the degree of h of x, we'll call it n. We don't know what they actually are. They could be tons of different things. We actually have 3 different cases for what they could be, and the degrees are actually going to tell us where our vertical asymptotes are. Okay, so if the degree of m is less than the degree of n, meaning that the degree of the top is less than the degree of the bottom, right, we're going to have a horizontal asymptote at y is equal to 0, or the x-axis. Okay? So if the degree of the top is less than the degree of the bottom, right, the horizontal asymptote is going to be the x-axis no matter what. Now, if the degree of the top is greater than the degree of the bottom, right, we're actually not even going to have a horizontal asymptote. Okay? Never will, because no matter if I simplify this thing down, or it's always going to simplify down to at least a linear function, so we're always going to have some sort of range that has an infinite number of outputs. Okay. Now, if m is equal to n, and this is the one that we've kind of seen more likely, right? This one's actually a lot more complicated because we do have a horizontal asymptote, right, at the line y is equal to a over b, where, right, a is the leading coefficient of g of x, and b is the leading coefficient of h of x. Okay. And that's kind of that's kind of where our asymptotes are going to be. So let's kind of take a look and kind of determine it. All right. So in these examples, we're going to simplify each function or each rational function and determine the restrictions on both the domain and range. So essentially, we're finding all holes in vertical asymptotes. Okay. So for number 1, all right, again, the first thing I want to do is I want to simplify this guy. So I'm going to go ahead and since I can factor the top, I'm going to factor the top. And so the top, if I factor it out, is going to give me x plus 1 times x plus 4, all over x plus 2. Okay. Now, I can't remove anything out of here, right? So that means that we have no removable discontinuities. So, right, we have no holes. Okay. What about vertical asymptotes? Well, x can't be 2 or negative 2, so we actually have a vertical asymptote, since we couldn't remove it, at x is equal to negative 2. Now, we want to determine where the horizontal asymptotes are. Okay. Now let's check. Okay. We're using kind of our rules, right? So we want to find the degree of the top. Well, since there's two x's, there's an x squared up top, so that means m is equal to 2, and n, in this case, is only equal to 1. The degree of the top is greater than the degree of the bottom, so in this example, we would actually have no horizontal asymptote. I'm going to make it a little bit bigger so it's because that's the one we're really kind of focusing on today. Okay, so we have no horizontal asymptote because the degree, I'll write that down here. Since m is greater than n. Okay. Moving on to the second one. Okay. Again, what we're going to do is we're going to simplify these out. Okay. So the top is already simplified, so I'm just going to have an x minus 1, and then the bottom is going to simplify to two numbers that multiply together to give me. Multiply together to give me -4, but add to give me +3. So that's going to be, what's that? X minus 1 times x plus 4. Okay. Now, because I can remove the x minus 1, all right, we're going to have a removable discontinuity, and I'm left to 1 over x plus 4. And I couldn't remove the x plus 4 from the bottom. So we actually have a hole at x is equal to +1. We have a vertical asymptote at x is equal to -4, and then now we want to check m versus n. So we have m, and again we always refer to the beginning. Okay, so in the first one we had m is 1 because that's our degree of m, and then the degree of n is equal to 2. Okay, so what's true is that we have the degree of the top is less than the degree of the bottom, which, going back up to our little chart here, says that we have a horizontal asymptote at y equals 0. Y is equal to 0, or the x-axis. Okay. Now, for number 3, and we'll check these on Desmos in just a minute. On number 3, we have -2x plus 6 over x minus 5, and we can actually, we can go ahead and simplify this out. I'm sorry, I want to use orange. Simplify this out, and we've actually got -2 times x minus 3 all over x minus 5. Okay. Now, again, we couldn't remove anything. So there's no holes. Right? We couldn't remove x minus 5, so we actually have a vertical asymptote at x is equal to +5, and then now we got to check the top and the bottom. Well, the degree of the top, m, is equal to 1. The degree of the bottom, n, is also equal to 1. So in this case, we have the degree of the top is equal to the degree of the bottom. So now what I want to do is I want to see, well, okay, that means that we have a horizontal asymptote at y equals a over b, where a is the leading coefficient of g of x and b is the leading coefficient of h of x. So essentially the leading coefficient, right, of the numerator over the leading coefficient of the denominator. Okay. So in this case, we want to check, okay, well, what's my leading coefficient? All right, a in this case would be -2, and in this case, b would be 1 because the leading coefficient is just 1. So we actually have a horizontal asymptote at y equals a over b, which in this case is equal to -2 over 1, which is equal to -2. So we have a horizontal asymptote at y is equal to -2. Okay, and that's kind of how we can determine this. So let's just go ahead and use Desmos to kind of check all 3 of these. 5x plus 4 over n plus 2. So go into Desmos. Hopefully nothing's up here. Okay, so our first one, we have x squared plus 5x plus 4 over x plus 2. We have f of x equals squared plus 5x plus, was it 4? Let me double check. X squared plus 5x plus 4 over x plus 2. Sorry, I'll keep going back. Over x plus 2. And you can see this weird, huge thing that we have here. And we said that we didn't have any holes. we said we had a vertical asymptote at -2, which we do. You can kind of see here if I kind of plot x equals -2, right? We have a vertical asymptote. Okay. And then we had no horizontal asymptotes, and that's hopefully pretty obvious for us to check. Okay. Now there is this other type of asymptote we call an oblique asymptote, but we're not going to go ahead and worry about those. Okay. So that was the first one. So it matched up with what we had. The second one is x minus 1 over x squared plus 3x minus 4. We have e of x equals x minus 1 over, sorry, I have to keep checking, x squared plus 3x minus 4. And so you can see in here, right, that we actually have, so again, we want to check since we had a little bit of everything here. So we had a hole at x equals 1 and a vertical asymptote at x equals -4. So let's double check that. So we're going to go to 1. Oh, yep, and we're undefined. We do have a hole here. We're going to go to, we have a vertical asymptote as x equals -4, which we can see. All right, and then we have a horizontal asymptote as the x-axis, which you can see. Okay. And then let's double check our last one to kind of see where that one is. -2x plus 6 over x minus 5. All right. Oh, is that right? Right. X minus 5. All right. So we have a vertical asymptote at x equals 5, and we have a horizontal asymptote at -2. Let's double check and see if that works. So perfect. We have, you can see that we have at x equals 5, we have, sorry, x equals 5. X equals 5, we have a horizontal or a vertical asymptote, and y is equal to -2 gives us a horizontal asymptote. Okay, so you can see that the algebra does work, right? And it does give us a lot of insight as to how we can graph these functions without actually being, without graphing them. Or at least we can tell all the important information of a graph using just algebra. Okay. Anyways, thanks for watching, guys. Good luck with the assignment today. I'll have another video using some more, or we're doing some more examples.